Hey there and welcome. We're constantly getting bombarded with claims and arguments and all sorts of data. So how do you cut through the noise? Well, today we're going to build ourselves a little toolkit for thinking more clearly. We're jumping into the basics of logic. All right, let's kick things off with a statement that I think you'll agree seems pretty straightforward. If an animal is a bird, then it can fly. I mean, it sounds right, doesn't it? But is it actually logically sound? And here's where we get to the heart of it. See, to prove that whole statement is false, you don't need some big complicated argument. All you need is one single example of a bird that can't fly. A penguin, an ostrich. And just like that, boom, the whole statement just falls apart. It's a perfect example of how what sounds right isn't always logically correct.
And this brings us to our very first tool, and it's a powerful one, the counterexample. It's all about finding that one exception that can completely shatter the rule. Okay, so let's get our terms straight. First, a conjecture. That's just a fancy word for any statement or educated guess that we're putting to the test. And our counterexample, well, that's our sharpest tool for doing the testing.
Now, think about the power in this. You could have 1,000 examples that seem to support a claim, but it only takes one single, perfect counterexample to prove the whole thing is wrong. That is an incredible amount of power packed into just one piece of evidence.
Okay, let's try this out for ourselves. Here's a simple conjecture for you. If you're eating a snack, then you're eating Doritos. So what's the first thing that pops into your head to disprove that?
Exactly. Popcorn, cookies, pretzels, an apple, literally anything that counts as a snack but isn't Doritos works. Every single one of those is a counterexample, and each one completely demolishes that original statement. See, it's that easy. All right, so this brings up a really important distinction we have to make in logic. We need to separate how an argument is built, its structure, from whether or not its conclusion is actually, true in the real world. So here's the difference. An argument is valid if its structure just makes logical sense. Our bird statement, if it's a bird, then it flies, has a perfectly valid if-then structure. But as we know, it isn't factually true. On the other hand, a true statement like triangles have three sides is both valid in its structure and, well, factually correct. Now, let's get down to the building blocks. How do we take simple ideas and combine them to make more complex logical statements? It really all comes down to a couple of tiny but super important words. What we're talking about are called compound statements, and the glue holding them together is usually the word and or the word or. You can think of these as the basic grammar of logic. They connect our ideas, and each one has its own very specific, very important rule. And these rules are awesome because they're so simple, but they are absolutely strict. And is the really demanding one. For an and statement to be true, every single part of it has to be true, no exceptions. Or, on the other hand, is way more flexible. For an or statement to be true, you just need at least one part to be true. Let's give this a whirl. So let's say statement P is false, but statement Q is true. When we connect them with and, that demanding rule kicks in. Since P is false, it doesn't matter what Q is. The entire combined statement has to be false. But watch what happens when we use or. Everything changes. Even though P is still false, it just doesn't matter. Remember, the flexible or rule only needs one part to be true. Since Q is true, the whole thing is true. And by the way, this tiny little difference between and or is exactly why you've got to read contracts and instructions so carefully. It can change the entire meaning of everything. Okay, reading words and symbols is great, but let's be real. Sometimes the absolute best way to understand how things are connected is to actually see it. And that is where Venn diagrams come in to save the day. Venn diagrams are basically a visual map for our logical ideas. Each circle represents a category or a group, and that awesome overlapping space in the middle, that shows us everything that belongs to both categories at the same time. They're just so intuitive. And check out the two key relationships you can show here. The word some, like some students are in both band and chorus, is shown by that classic overlap. But a statement with the word every, like every apple is a fruit, looks totally different. The apple circle is completely inside the fruit circle. It shows the relationship is absolute. All right, theory is great, but let's put this stuff into practice. We can use one of these diagrams to solve a puzzle and actually make sense of some real data. Okay, so here's our scenario. A survey of travelers and the cities they visited: Paris, London, and Barcelona. First question for you: how many people visited London and Paris? So take a second, look at the diagram. Where do you think that answer is hiding?
To get the answer, you've got to look at that entire space where London and Paris overlap. That includes the people who only went to London and Paris, plus the people who went to all three. You add them together, 64 plus 24, and you get 88.
Okay, round two. A little trickier this time. Using that same diagram, can you figure out how many people visited all three cities? Where would we look for the super travelers who did the whole shebang?
For this one, you gotta look right at the heart of the diagram. It's that one sweet spot in the center where all three circles, Paris, London, and Barcelona, all meet up. And that number, 24, represents the people who visited every single city.
So there you have it. In just a few minutes, you've got yourself a brand new logic toolkit. You know how to challenge a claim with a single counterexample. You know the strict rule for and the flexible rule for or. And you know how to use Venn diagrams to literally see how data is connected. So I'm going to leave you with a question to chew on. What's a common statement or belief that you hear all the time? One you've always just accepted that might have a simple counterexample hiding in plain sight? What are you going to start to question now?